Carlo Cavazzoni. I'm developing quantum espresso since more than 20 years so far. I started to work on quantum espresso here in Trieste in 1994, 1995. Now I'm in Cineca, which is Italian largest supercomputing center, and I'm responsible for quantum espresso of the parallelization paradigm. And in general, in Cineca, I'm working in advising communities in parallelizing application, and I'm steering the process of the evolution of the design of Cineca architectures. So first of all, the first part of the lecture will be to give you a presentation about what next. What is happening at the level of the evolution of high performance computing? And what are the challenges and what are the opportunities in the evolution? Obviously, high performance computing is relevant for material science codes and quantum espresso and also the other. Just because if you take the load, the average load of supercomputing around the world, probably the largest fraction of this load is represented by quantum chemistry code like quantum espresso. So today, a large fraction of investment in high performance computing is due to make computer cycle available for quantum chemistry codes. So there is a sort of positive feedback loop. So quantum chemistry code needs faster computer, and who is designing and procuring high performance computing have to satisfy this demand in computational need. So let's look at what's next. So we are in a very well, complex but at the same time interesting time frame, because something it will change in the future, and nobody really knows exactly, and we will discuss in this lecture what's next, how the next computer will look like. So I would like to start discussing the famous Moore's law, which is an empirical law that relates different things. So it's an exponential law that it has been applied to semiconductor industry in different flavor in the past. So probably the most famous version of the Moore's law is the one that everybody knows for the past. That is that the number of transistors per chip double every 18 months. So this has been, you can see, it was true since the 70s, and here you can read all the processors that have been put into the market along here in the last 50 years, and this law has scaled for well, 6 orders of magnitude, which is impressive. So, and this is still somehow predicted to scale, and we will see to what extent. Then there is another version of the Moore's law, which is applied to the power of supercomputer. This picture represents the let's say the statistics of the top 500 list. The top 500 list is the list of the 500 most powerful supercomputer of the world. And the green one is the integral of the power of all the supercomputers in the world. The orange triangle is the most powerful supercomputer of the world. And the blue square represents the supercomputer in position 500 of the list. So there is, again, these exponential trends appearing all over the year. So supercomputers around the world still continue to have an improved performance over the time. Now the most powerful supercomputer on the Earth has more or less 100 petaflop. The supercomputer in position number 500 has more or less few hundred of teraflop, which was the power of the most powerful supercomputer in 2007. So in 10 years, let's say the commodity supercomputer, because the computer in position 500, it could be a supercomputer that stay in the department of your university, usually, in terms of more or less size, has the same power of the supercomputer, of the fastest supercomputer on the Earth 10 years ago. This is more or less the fundamental exponential law that is behind the evolution of supercomputers. So again, and if you take a laptop computer today, a laptop computer has the same power, more or less, of the fastest supercomputer of the world in the year 2000. So in 15 years, what was the power of the most powerful supercomputer in the Earth, you can find it in a laptop. Okay. So now, what is obviously the question everybody is asking? This trend will continue. So in 2030, when we will do the same workshop in 2030, your laptop will have the power of the most powerful supercomputer of today, as it has been in the last 15 years, or not? And if yes, how it will look like? Okay, this is the question. This is important because this will tell you how easy or how tough will be to write the codes not only for the supercomputer, but even for your laptop. Because otherwise, usually what we did 15 years ago in the most powerful supercomputer in the world, you have to do today in your laptop in order to reach the same level of performance. So the question is, what we are going to do next in the application, in the supercomputing, to being able to use even your laptop in 15 years from now with this kind of application. But now we have seen two pictures of the Moore's law where things seems to go pretty well. So everything is going like in the past, and nothing seems to stop these trends. Well, as I said, something is going to change. And this is the first sign that something is going to change. So when we look at the Moore's law, not only about the number of transistors, not only about the power of computers, but about the dollar, something is start to change. We have a problem. So what is the problem? The problem is that the cost of making transistor is not decreasing to keep the pace of the power improvement of the chip itself. So at the end, what happened? That the cost per transistor remain almost fixed. Okay, you can make faster chip with more transistor, but you have to pay more money to get them. So in the past, this curve was assuring you that you can buy a new, faster chip at the same price of the chip you bought 5 years ago. Now it's no longer true. If you would like to have a chip which is faster than the chip you bought 5 years ago, keeping the Moore's law improvement, so having the chip 4 times faster, you have to pay more. So this is making things more tough from the point of view of the acquisition. So a simple demonstration of that. So nowadays, well, in most laptops you have 2 core chips, okay? And so it was 10 years ago. But, so the peak performance of the processor is still improving, but the 2 core chip is no longer the best, what is called the best version of that particular processor, okay? Because you have, let's say, chip with not only 2 core, but 4 core, 8 core, 10 core, 12 core, now 20 core, 22 core, okay? So the 2 core chip has 10 times the power of the 2 core chip of 5 years ago. Not the 2 core chip you buy. Yes, it's a little bit faster, but not following the Moore's law. Okay? You are able to follow the Moore's law only if you buy or if you are able to integrate core or chip with much more core. Now, what is the fundamental reason of this behavior, so of these trends? Why is the cost now not going down, the cost per transistor going down at the same pace as in the past? This is because of another law, which is the so-called Dennard scaling law. The Dennard scaling law relates a few simple macro characteristics of the integration process used to make the transistor itself. So this is the so-called very large scale integration technology, which is the technology used in all the factory where they really produce the silicon chips. So L is the length of the transistor, V is the applied voltage, F is the frequency, D the density, and the P the power need to make the the electrical power that is used to make the chip work. So L are the values of the transistor for a given generation of the very large scale integration. L prime, V prime, F prime are the value for the new generation of the very large scale integration process. These all the new generation are the so-called downscaling processes that you maybe have heard, the 22 nanometer, the 18 nanometer, 14 nanometer, so on and so forth. So when you downscale a transistor for a given generation to the new generation, usually you make it smaller because in order to have more chip, more transistor in the chip and to have a faster chip. So this law was predicting that you can halve the size of the transistor, halve the voltage of the transistor, V, from one generation to the other, doubling the frequency and keeping the same electrical, the same power. This was true for many years in the past, and it has represented the successful, the element for the success of the microprocessor taking over in the HPC business. So Intel microprocessor, as well as other, thanks to this fact, was able to double the frequency, so the power of the chip, every 2 years, using the same power. This is no more true because now the chip are working to the so-called near threshold voltage. So in a near threshold voltage chip, you have a supply voltage which is really close to the conductor insulator threshold in the transistor. So you cannot halve the voltage any longer, otherwise the semiconductor will become an insulator and you do not have any propagation of electrical signal, electron, and so you cannot build a digital chip with it. So now we are in a situation which is more like that. So where from one generation to the other, the voltage is more or less the same, the supply voltage. We cannot lower the voltage any longer. So we can still, in principle, double the frequency of the chip, of the transistor. But this will cost us an exponential growth in the power drawn by the transistor itself. Okay? And this is no more sustainable because today, in a modern silicon chip, you have more heat density than in the sun surface. So there is more heat density in a silicon chip than in the sun surface. So you can imagine, so if you would like to build a chip which is even faster based on silicon, or either you keep it cool with an excessive amount of cooling capacity, or either the chip itself will vaporize immediately as soon as you start to make it work. So this is the so-called power crisis. So we do not want to build a chip that vaporizes itself when you turn on the computer. So what is happening is that now it's 10 years that the core frequency do not increase any longer. So the typical working frequency of transistor stay in the range of few gigahertz and do not increase any longer. Okay? So at the end, to keep the Moore's law in place, the solution has been, well, instead of increasing the frequency of the core, let's start to increase the number of cores. So it's 10 years that the working frequency of transistor do not increase too much, but we are seeing that from one generation to the other, the chip feature more and more cores. That the next generation, now we are seeing a processor with tens of cores. And the trends will continue. And this is, well, we turn an engineering problem, which is the power crisis, with this trick into a programming crisis. So we move the problem from the size of engineer that designed the chip to those that have to use the chip. Because as we will see in a minute, this increased number of core put pressure on those that design the application. Because you have to increase the parallelization of your application. So in order to be able to use the new chip, suppose you spend X money to buy a new, most powerful chip. But if you do nothing to your application and you simply recompile, the performance of your application today, most probably, is lower than the same application in the chip of the previous generation, if you do not work to improve the parallelism, the parallelization of your application. So you can, you are able to take advantage of new chip only if you are able to refactor and make your application more scalable. Otherwise, already today, your application, and you can prove it very easily, most probably run slower on the same core, on the same number of core. There is another problem. And the problem is the following, that if we take a silicon lattice, the lattice, the interlattice distance is 0.5 nanometer. Today, the transistor inside the chip are 14 nanometer. Now they speak to make a chip with transistors that are 10, even 7 nanometer. But the problem is that in this range, you have only 50 atoms. So we are in a phase where, or soon we will reach a limit where a single defect, so a single misplaced atom in this transistor will break the transistor. So another challenge, and it is the reason why the price is not going down, is that the number of non-defective chip exiting the production line is decreasing. So a few years ago, all the chip that were exiting the production line were good chip to put into the market. Today, because we are at the limit, we are closing the gap between the limit, the physical limit of the technology, the number of defective chip produced is increasing. So out of the same amount of time, the same silicon crystal, the number of good chip is decreasing. So since the processes do not decrease in terms of overall cost, the cost of the single piece is increasing. So someone said that we can, from the technological point of view, we can think to reach 5 nanometer, probably. But the questions start to become, it will be economically sustainable, or producing a chip like that will cost so much money that nobody will at the end. So the market, in order to sustain the silicon technology market, you need to produce this kind of chip in billions of components in order to pay the investment for the next technology cycle, or for realizing the fab, the industry to make the chip itself. So the question is, will the price of that chip low enough to sell this chip in billions? If not, we will never reach this figure, because probably to make a new fab, a new let's say industry to make this chip will cost billions of dollars. So either you are going to sell billions of pieces, or it will not be economically sustainable. Okay, this is about the fundamental physical process behind the realization of silicon chip. What is happening to the application? We say, from a point of view of the overall business, we move a problem related to the engineering of the fabrication of the chip into a problem of those that write application. So we are moving from a power crisis of the chip. We sort of work around this power crisis, but we simply take the problem from there to those that have to write application. So now we are in a programming crisis. So how large is this crisis? Very large. So, but before understanding how large is this programming crisis, we need to introduce this Amdahl law. So Amdahl law says a very simple thing, a very simple truth. So the scalability of your application is intrinsically limited by the serial fraction of your application. So the fraction of your application that you are not able to parallelize. So the serial fraction, by definition, is the portion of your application that whose whole time does not increase in the number of CPU. So as the number of CPUs goes to infinity, the parallel fraction of the application goes to 0 in terms of whole time. But the serial fraction do not change. So basically, the maximum speed up you can reach with your application is limited by the size of the serial fraction. So the math we have to do, everybody has to do, is the following. If my application scale, suppose up to 8 CPU, and I'm not able to reduce the serial fraction of this application, it is worth to port this application, to buy a chip with 16 core. Well, yes, if I have to run twice this application, but from the point of view of the use of this application, this will never scale. So the time to solution of this workload will never decrease, even if you buy a 100 core chip. Okay, let's move to, so what we have seen so far, that the peak performance of the supercomputer or of the chip as well is still increasing, and we are heading toward the so-called exaflop system. So a system where the peak power is in the order of 10 to the 18 floating point operation per second. Now, if you remember, the number one of the top 500 is just one order of magnitude less, so 100 petaflop. But because of the Dennard law, the performance of the transistor is not increasing. So the frequency of the single transistor. So the performance of the single FPU, so the floating point unit, so the part of the chip where floating point operation are performed, is not increasing any longer. So we are close to 10 to the 9 floating point operation per second, because this depends only on the frequency of the FPU. And this is the Dennard law. So you can do the math yourself. So I don't know how the next supercomputer will be. I really don't know. Nobody knows. We will discuss a little bit what are the trends. But I know one thing, and I'm sure. It will feature 10 to the 9 floating point unit. I don't know how they will be placed inside the supercomputer, how they will be organized. There are several receipts, but I'm sure there will be 10 to the 9, or a number close to that. So the problem is, if I have to code an application to scale to the full system, my application parallelism have to become so large that the serial fraction of my application has to be less than 1 part in a billion. So this is the measure of the size, how big is the problem in the programming side. So the programming crisis is terrible, okay? So let's start to now discuss how these FPU are going to be placed in the chip, okay? So there are few roadmaps, and we will try to analyze them. So first of all, we have to understand that now, because of the Dennard scaling law, traditional RISC and CISC chips are designed for maximizing the performance of all possible workload. If you have to design a new chip, or, well, in the past, the design of the chip was so that you could gain performance in all the application, in all the possible workload that are going to run on that particular chip. So unfortunately, because of the Dennard scaling law, maximizing the performance of all possible workload means investing a lot of chip, a lot of transistor in making complex circuit that have to deal with complex instruction sets. Okay? Caches, a lot of units to have prediction of what is the outcome of conditional instruction. You have a lot of units to deal with what is called a speculative execution, so to try to guess what's next. So a lot of circuit is dedicated to maximize also the single thread performance. So, because you as a customer of chip, you would like and you are happy if you see that your scalar code or executable, when it is run in a new chip, run faster. How faster is another question, but at least faster. So to make this work, you have every time increase the so-called, let's say, call it hardware tricks that make your application run faster in the chip itself. Unfortunately, so if we would like to use this kind of chip to include 10 to the 9 floating point unit, the power taken by this chip will break any data center capacity. So if you do a simple math, taking today's chip that includes in the order of 100 of floating point unit, okay, and you project the power of this chip, including hundreds, to the level or to the size of a computer with 10 to the 9 floating point unit, the power taken by this computer will be larger than or in the order of 1 gigawatt. Okay? So there is no way that we can use traditional chip design to build a computer with 10 to the 9 floating point unit, because in that particular design, the density of floating point unit is not high enough. And so I will need a couple of nuclear power plants to make this computer run, so it's not really feasible. So the change in the paradigm is the following. So instead of thinking of having a chip where I optimize the chip for all possible workload, I start to build chip designed to maximize performance in a small set of workload, and in particular floating point operation. So I can simplify my core design to have a lightweight core in the chip, so that at the end I have simple functional unit with a poor thread performance maybe, but I can stuff a lot of them in a single chip. And so I can eventually maximize the chip throughput for that particular workload, and in particular floating point unit. So at that point, at the end, I will be eventually able to limit the power taken by my computer for that particular workload. And if we look at the possibility available now, what is really happening in the market in the integration of supercomputer is that we have two models basically to realize this supercomputer. One is so-called hybrids, or better heterogeneous system, where you have traditional RISC and CISC chip together what it is called an accelerator. So you do not rely on the traditional chip to reach the 10 to the 9 floating point unit target. So you keep the minimum number of traditional chip in your system to make it run, and at the same time in order to maximize the throughput, you use accelerators, so chip that is designed to make just one thing, floating point operation. Or in the other hand, you can have a different model, it is homogeneous, where you have a compromise. You have chip in the system which are all the same, but are not like the traditional RISC or CISC chip, have a different design, much more simpler, with, again, much more floating point unit. And if we look at the last top 500 list, you can see that those systems are start to pop up in the top 20. So here in green you can see system which feature those GPU kind of accelerator, and system in light blue, so-called many core system, where you can find the other architecture design that maximize the throughput for the floating point. So the white one are the computer realized using the still an approach which is somehow old style, but most of them are computer like this one. These old blue GenQ system are not going to be upgraded any longer because this architecture design is dead. So IBM is not going to produce a new blue gene follow. So these places are going to be soon going out. And the first number one is somehow a different design, but in a way which is probably an extreme or a different version of this architecture design. So, well, we see one of the, we say heterogeneous. When we speak about heterogeneous, we always think about having two different chips working together in order to maximize the performance. So a traditional CPU with traditional design that is not enough to maximize, to have a high throughput of the system, and an accelerator. The accelerator can be many different things. But in any case, here the problem will soon become the bottleneck between these two guys. So you can do a lot of things. And today, what is happening is that there are architecture design that are working to make this communication channel, this bus, larger and larger enough to allow for seamless memory transfer. So what is the problem here? The problem here is that the bandwidth linking these two guys is less than the bandwidth linking the memory to this guy. So if I have to transfer work to this accelerator, this ends up slowing down the transfer rate between the main memory and the floating point unit. So, or either I keep everything inside these guys, so I start computation here and I stay here forever, or if I have to transfer from the main memory to this guy data, then I'm going to be limited by this transfer rate. So you can work on it, and there is now solution for that, where you make this bus larger so that the bandwidth you have here is comparable to the memory bandwidth. At this point, if I have to transfer data from the main memory to the accelerator, it looks like the same, I have to transfer data from the main memory to CPU. So you are not going to pay too much penalty. Or you can have a different design, like the so-called AMD APU or the ARM big little design, where you have the CPU and the accelerator integrated as different core of the same chip. Okay? In this kind of design, you do not have any longer the problem of the memory transfer, but there is another problem, that is the overall optimization of the architecture design. So each of these two guys compete for the silicon transistor. So at the end, this is very efficient design for very low power system. Well, this is used in this design is used in most cell phone, where you have a GPU integrated with a CPU, or in gaming console. All the gaming console have this design. Okay, either using APU or now the so-called Tegra chip, which include again an ARM and an NVIDIA GPU in the same chip. But if you have the goal to optimize the architecture, these are limiting you, because when you optimize for the high maximum throughput per chip, it is better to have a pure, let's say, GPU chip or a pure CPU chip, because the competition inside the same design is somehow limiting both sides. And at the end, if you perform an optimization versus if you would like to optimize both the peak power and the chip size, you end up that this design is better than this one. If you would like to optimize the peak performance and the power, then this design is better. So other direction is those taken by, in example, as we will see in a minute, by Intel or other, building the so-called SoC, so system on a chip. Again, here the idea is to minimize all the possible memory transfer, because memory transfer are those operations inside chip that cost energy, because if you have to transfer data, you have to somehow move electrons from one transistor to the other, and these are, moreover, you have to move electron across copper wire, and this costs energy. Okay, so people trying to minimize this energy. So now there are technologies that that allow that. Let's say, in particular, this one. This is sort of next to come, the photonic. So to substitute copper white with photonic line, but this is not feasible yet. So photonic is used for long distance communication, but at short distance, copper is still more efficient and more cost effective than optical communication. But so photonics is probably next to come to overcome this limit. But now we have this so-called true silicon via that allow you to couple chip together using semiconductor, direct semiconductor to semiconductor connection. So silicon to silicon connection. So these allow you to perform the so-called 3D stacking of chip, so to glue chip one over the other. This is a very amazing technology. This is featured by both Intel and NVIDIA, as we will see. And if you look at the chip, it's amazing how you can see that they really solder chips one over the other, and allow you to, let's say, to reduce the limitation of having electron moving through copper wire, and at the end allow you to have memory directly soldered on the chip together with the CPU, so you do not have any more or any longer off-chip memory components. And this will increase the memory bandwidth and will lower the memory. It has increased the memory bandwidth both on the latest GPU and on Intel chip by a significant factor, and reducing the power need to transfer data. Well, if you look to go a little bit more further with this discussion about how this architecture really look like, this is a sort of design. Well, one is, let's say, the heterogeneous model. We say the heterogeneous model combines a traditional CPU, I will not discuss, and an accelerator. How an accelerator look like? So here I have an NVIDIA, let's say, a design of an NVIDIA GPU, but for AMD GPU, it will be the same, or any other GPU, it will be the same. All the green rectangle are cores. So in an NVIDIA GPU, you have thousands of cores. Each core has a floating point unit or a couple of floating point units. So the design of the GPU, you remember, we need to reach to 10 to the 9. So using GPU, in a single GPU, I may have 10 to the 5 core or FPU quite soon. So 10 to the 9 minus 10 to the 5. If I have 10 to the 5 in a single node, well, I can build an exascale machine using 10 to the 4 node, which start to be probably feasible. Okay? Today, supercomputers have number of nodes in the order of 10 to the 4. So this look like being a good design for building supercomputers that feature 10 to the 9 FPU. And here, what are the three? So this core is so simple that is not even independent from the other. So each of these core cannot execute an instruction which is independent from the other core. So it does not have a so-called its own decoding unit. So this guy shared the decode of the instruction unit with other cores. So they work in pool. So each core cannot execute an independent instruction from the other core. They have to work in pool with the other. So what does that mean? It means that in order to get to take advantage of this design, I need to use a programming model, and we will discuss in the second lecture, such that I schedule, I will be able to issue a single instruction over multiple data. So I need to schedule a single instruction working on multiple data. How many data? For the design of the NVIDIA GPU, at least 32 data using the same instruction. So this is a closer loop to the NVIDIA GPU. Well, another important feature is that the overall design is it is a hierarchical design. So hierarchy is more and more important in nowadays computing. The hierarchies inside the architecture, both at the level of execution unit and the memory, is increasing, is becoming deeper. And we need to get advantage of this hierarchy, otherwise we will not be able to exploit the power of the CPU. So again, you see, these are the core. Then there are some shared unit, and I have a different level of cache at the level of this so-called streaming processor, then a memory which is dedicated to a given just one purpose, so the texture memory. So I do not only have a specialized core. In order to maximize the design, the performance of this design for a given particular task, I need also to specialize memory chip for a particular task, not only and for the GPU it's texture. So you have memory for texture. So what is the other design? The one, let's say, that now is, well, promoted by Intel, but soon also other will follow with similar design. And this is, well, a sort of compromise between traditional SIP and GPU. And this chip is called Xeon Phi. In particular, the last version of Xeon Phi has a code name Night Landing, which is start operating in different HPC center, Cineca as well, in this month. So it has been released in the middle of last year, becoming production at the end of 2016. And, well, the Night Landing work using, again, a different design with respect to traditional chip, and in particular, it is a sort of cluster in a chip. So in order to realize a microprocessor which maximize the performance, they use simpler core, but these core are, let's say, are light core, but not so light as the one that are used by NVIDIA GPU, which cannot be independent. They need to live in pools. Instead, the design of Intel have light core. Basically, the core of these guys is it's the basic design derived from Atom chip. So the same you may find in tablets or in phone. So the core is the same, optimized for power consumption, but it can work independently from the other core. Now, since I have to put so many core inside a chip in order, again, to reach, to have the possibility to have 10 to the 4, 10 to the 5 FPU in a single chip, because this is the more or less the size in terms of FPU I need to have in a single chip in order to be able to build a supercomputer with 10 to the 18 FPU in total. Sorry, 10 to the 9 FPU in total. So I need to build, let's say, a network. In particular, these guys, so let me see if I do not have so you have all these, yes, all these boxes are cores, are Silvermont architecture. Silvermont is the code name for one of the latest core Atom processor. So I have all these atoms, all these processors that are like the one that you may find in tablet or in cell phone, connected with a network, with an internal 2D network. And then I have of the so-called MC DRAM, which are memory chip already integrated in the package. So as I said, this is an amazing piece of innovation where now we do not have, well, at the end you need also memory, off-chip memory, because these guys, these memory chips that are integrated together in the same package, so you do not see the memory because it's integrated in the same package, has now the limitation to be in terms of size, because it's up to 16 gigabytes in terms of size. And moreover, I can even integrate in the same chip, I can even integrate the network controller. So this is another innovation in the same package. So I do not, beside the chip itself, I can make a computer without anything but the chip itself. Being the chip, including both cores, memory, and network fabric. So I only need a wire exiting from the chip in principle. So the innovation included in this design are two, the main innovation. One is this, the so-called on-socket memory. So you have memory chip with very high bandwidth, with a peak memory bandwidth of more than 400 gigabytes per second, so 4 times larger than the one you have off-chip, included inside the chip itself. Then obviously, if you would like to have more than 16 gigabytes, you may add DDR4 memory, and DDR4 memory is obviously off-chip as all the other chip design. And the other innovation is the so-called AVX 512. So in order, which is a vector unit, a new vector unit, larger vector unit. So in order, again, remember, we need 10 to the 9 FPU. I cannot build a supercomputer with much more than 10 to the 4, 10 to the 5 nodes, because then it will not be affordable in terms of sizes and power consumption. So I need to stuff 10 to the 4, 10 to the 5 FPU in each single node. Using GPU, you can do that using this tiny core. With this installed Xeon Phi chip, you have two things. You have much more core, you have atom core, but each atom core, it does not bear only one FPU. Each core bears 2 vector units. So which is the characteristic of the vector unit? Let me see if I have, no, I need to speak them afterward when we speak of the programming model. But basically, again, a vector unit is a floating point unit where you have a single instruction working on many different data. So a vector unit is able to perform in a single clock cycle the same operation, a product or a sum, on multiple data. Again, so It's a sort of a small, this AVX512 at the end is a sort of a small streaming processor you see in a GPU. So again, at the level of a FPU, floating point unit, you do not have independence of extraction. In order to use this new unit that allow you to reach, well, teraflops for each chip, you need to rewrite your application such that you have the same instruction acting on more data. And this is the same we have seen with the GPU. So at the end, when we come down to the floating point instruction, the most basic principle is single instruction on multiple data. Because the coding instruction costs too much. So traditional chip, if you remember, we speak about traditional chip that optimize the execution of single threads. In order to maximize the performance of a single thread, I have to make my decoder of instruction or whatever is such smart enough in order to improve the scheduling of instruction. But this costs too much in terms of energy and transistor. So if I want to maximize the throughput, then I have to reduce the amount of transistor used in decoding the instruction, managing the application, and leave room for transistors that do useful work, floating point instruction. In the case of floating point or multimedia or whatever is your specific design. A sort of multimedia and floating point instruction are close enough, luckily, for floating point, for HPC, gaming, multimedia, and scientific application, luckily, are close enough in terms of workload that we can, let's say, take advantage of all the investment going on in the world to optimize for entertainment and media. Okay. Otherwise, floating we will not see any possibility to make a faster and faster supercomputer. Okay. So to go a little bit deeper in this new technology with their own package memory. So the own package memory, the other beautiful thing is that you can use it in many different ways. And the operating system may be configured to use it well, in the so-called flat mode. So you can configure the operating system to use the on-chip memory as well as the DDR memory as they were a single address space. Well, this is useful if you would like to have to see the chip with a larger memory, but does not usually help the performance. Or you can use it as a cache. So this becomes basically a cache to the main memory of the system. So your application works basically on this 16 gigabyte replica of the main memory. And if you are good enough in making the computation as local as possible, local means that most of the computation happen to be to happen on data that are close in memory address space, or stay close, stay in the same range of address space as much as possible. Obviously, it cannot be done in absolute, but there are techniques to localize the access to the data. Well, you can really work as if you had a bandwidth that is 400 gigabytes per second and not 100 as it is the bandwidth of this guy. This means in many cases having a performance which is twice or 4 times as the performance you got using only the main memory. So we are doing experimentation in our system which feature this kind of chip. And if you have an application like Quantum Espresso that is able to take advantage of this hierarchy, the difference between these two modes is more than a factor of 2. So using this mode and working with this memory allow you, even if the core is very weak in terms of, with respect to the standard Xeon core, this core in terms of single thread performance is weak, but thanks to this fast memory channel, you can compensate, and the performance at the end are not so different from that of the Xeon core. Or you can have a hybrid mode, where you have a cache mode, and you can partition this memory into one part used as a cache and one part used together with the other. I would like to skip, well, we do not have time to discuss the roadmap, but these are, well, new data I've recently started to collect using this kind of chip. And this is the comparison in terms of using different metrics, the comparison of the performance using this new chip design, this KNL, that is Xeon file, and traditional Xeon multi-core chip. So this Broadwell, this chip in particular is a 18-core chip, and in terms of, you remember, we discussed about price, is the so-called top bin, or, well, among the top bin, so the most costly chip of the Xeon product line. A single chip of this costs $3,000, more or less, single one. So we are comparing the performance of this top bin traditional chip with night landing. So if we take cores as a metric, and this is the second taken by the simulation, we can see that Broadwell, so Xeon traditional chip, taking the core performance is a little bit faster than 20–30% faster many times with respect to the KNL single core chip, because we said in Xeon 5 the core are lighter, but we have many cores. So here we have 18 core per chip. With this guy we have 68 core per chip. So 4 times the number of core in the same silicon, because at the end the production process of these two guys is the same. The size of these two guys is the same. What changed is the lithographic process, that in one they change only the bit mask of the lithography in order to produce this guy or these guys. So the differences are basically coming only for the architecture design. So if we take the single core, obviously the Broadwell traditional design, as expected, is faster. Okay? But if we take the node as a metric, so let's measure which is the throughput of the node, the situation starts to be different. KNL, a single KNL node, is faster than a single Broadwell node. So here we can see that the two architecture, the working principle of the two architecture, what is the net effect? And even more, if we take the power used to make this guy work, so the two chips do not consume the same amount of power. A node running KNL, Oxygen 5 takes 315 watt. A node running a Broadwell node, which is 2 chip, takes 450 watt. So at the end, if you measure the power you need to boot to make this guy run, well, the situation again, you have a significant gain in terms of power efficiency between these two guys. So making this the architecture design, well, more appealing to design a computer that otherwise, using this other chip design, will take hundreds of megawatts up to, well, the limit of 1 gigawatt in order to be built. Not that this guy will consume do not consume energy. So we now, in our system, which is 11 petaflop, 10 petaflop, let's say, it takes 1.5 megawatt. But, okay, so if you do the math up to the exascale, we come down from gigawatt to 100 of megawatt. Well, pushing this design further and making further optimization, maybe at the end we can have the opportunity using this kind of design. For the GPU is exactly the same. It is the arguments are exactly the same. You can have the possibility to build a machine with 10 to the 9 floating point unit, not drawing the electrical power of an interior power plant, nuclear or any other power plant. Okay, I think we can close the lecture here and start again afterward with the paradigm. Yes?
This is a benchmark for the
yes. Yes.
Have you done it also with
yes.
WSF? Is the picture the same? And have you tried with the real system application?
Is a little bit worse.
Yes.
So the problem with PW is, well, the Carlo kernel is very well suited for this kind of chip because it's less memory bound at the PW. So the picture, if you want, I can display it. I should have it with me. But the trends are confirmed. So let me check.
Do you have to change the code, or it's exactly the same?
No, this is we have only optimized the parallelization parameter and compile using AVX as a target architecture. Yes, only compilation. Well, the code has been refactored in the last year in order to be prepared for that. Let me check. Both. Why I don't see the... In the second lecture, we will discuss deeply this. But I just want to check if I have a Google. This is why I do not have network. Let me check. should have network. Okay. So this is well, this is a little bit outdated because I optimized the execution a little bit. Let me check if I can get the outdated version for that. This is exactly the same test, but using PW, a large PW. This is with the number of core. You can see difference. This is traditional KNL. This is traditional core, and this is the KNL execution. So yes, you have more or less a factor of, not a factor of 2, but between 1.6, 1.7. If you take nodes, well, in terms of nodes, let me check if I can, because in my I also see the subgrid. Unfortunately, you cannot see the subgrid, but the difference is between this guy takes 500 and this 600 seconds, more or less, using the same amount of nodes. So you are going to pay a little bit of penalty. We need to work on that, obviously, because we expect here, okay, is that okay to have not a factor of 2, because this is 500, this is, yes, this is 600, this is almost a factor of 2 you have here in terms of penalty. But this is more than what we expect in theory. Here we have, well, 15% in terms of 20%. And the things become, well, more or less the same in terms of power. When we go to make the math in terms of power, the two architectures are, for what concerns PW, they are equivalent in terms of energy efficiency. So with Carparinello, there is a significant, with the Carparinello kernel, there is a significant gain using KNL. With PW, they are equivalent. They are equivalent also in terms of cost, because a CPU hour costs less than 1/2 the CPU hour on the Broadwell node. So they are so far they are equivalent. But as we discussed in the second, we need to work to take advantage of the new architecture. But I'm pretty much sure that because you have also to consider that here we compare execution with, you see, here we are using almost 10,000 core. So if you run an execution, maybe where the code scale properly, and where you are memory bound, much more memory bound, probably the difference will be smaller, and the situation, I'm pretty sure, will not be so different using GPU at the end. This will be discussed in the next. Yes?
So on your slide on the KNL effects, you show the set that you call the core length per core.
Mm-hmm.
So you mean there are 68 cores, and each of them. Now, in scientific code, I mean, multi-threading is not the case with the line per core. So my question is it different on this very new and kind of stable paradigm of the architecture? Is it now getting like feasible to use multi-threading, or is still that we never use that for, I mean, we never use for threads per core, and we still set one thread?
So first of all, there is an hardware support for this multi-threading. So you have dedicated hardware for each of the 4 threads. So there is no penalty in keeping the hyperthreading running. There are probably some issues with the operating system that are not ready to deal with. We are running CentOS on this system, plain CentOS out of the shelf, almost out of the shelf. And we are seeing some probably problem in dealing with threads because operating systems are not designed to deal with 272 virtual cores. So there is probably room to optimize the scheduling of threads. From the point of view of the application, you do not need 4 threads to use all the floating point unit. So if you vectorize properly, just 1 thread per core is enough to fully load the vector units. So the problem is there are many workloads where this is not possible because as we will discuss next, in order to load such vector unit, you have to schedule 16 floating point instructions at the same time. So either or your loop are so large and your computational chunk are so large that you can decompose them into large chunk, or otherwise many workloads, if you do not are able to do that, you cannot load the floating point unit. Multi-threading can be a way to mask the latency of the load process of the floating point unit. So if you have very, call it high throughput like workload, I have one that I'm using that is molecular docking, mechanical docking, and then you can really see that using hyperthreading, you can obtain a significant improvement in performance because docking is trivial mechanical geometry computation where the loops inside the most scheduled, so the extraction which is scheduled all the time is the Pythagorean distance. So you cannot vectorize the Pythagorean distance over 16. Well, there are ways, but this makes things much more complex. Okay. Oh, let's do the break and in half an hour less. Okay.